Welcome to Midnight Coding, everyone. Today we'll solve LeetCode question 684, redundant connection. This is a graph problem, and we'll be using union find algorithm to solve this problem. But before we continue, please like this video and subscribe to the channel, as it'll provide you with all the luck you need on your upcoming job interview. So if you're planning on getting into any of the FAANG companies, or if you have an upcoming interview, if you like this video, I promise you will get the offer. And also, it encourages me to keep making educational videos like this. This is a medium difficulty problem, but before we continue with our explanation and coding it up, I want to go over the concept and explain to you guys how exactly union find is helpful in this situation and how we can optimize union find. So let's jump into the explanation. Now let's think about how union find or disjoint set with rank works. In the beginning, all the nodes are going to have rank of 1. And when we connect two nodes, it doesn't really matter which one is going to become the parent node or the root node. So let's just say that I'm going to make this one the parent node. So this one is the parent node, and since we have made that one the parent node, let's update the rank. So the rank of this one is going to be 2, and this one is its child node, and this is the parent node now. So now when we connect this node over here with this node over here, now we ask, what's the parent of this node? So we can go up and we can see that the parent node of 1, this one over here, is 2, this red one. And we're gonna check the rank. So the rank of this is 2 and the rank of this one is 1. And we're gonna do the same thing with this node over here too, and we're gonna try to find its parent node. And how do we do that? Well, we know that this node is the parent of itself because of this connection. So we can just imagine that all the nodes starting out, they're going to be their own parents. So now, after we have done all that, we know that the parent of this node is this 2 as well. And we can just keep the rank as is. So let's do the same thing with the second half of this graph. So let's connect these two and let's make its rank 2, and let's connect these two. And now, what if you wanted to connect this one and this one? So if you wanted to make a connection between these two, first of all, we're gonna find its parent. So we're gonna go up, and we found its parent. Its parent is 2, and then we're gonna go up again, and this node's parent has a rank of 2 as well. So as I said again, if they're equals, it doesn't really matter. We can just connect these two like that, and then we can make the parent of this set to be this node, and then we will just update its rank as well. So to do these operations, we need two functions. We need a function called find, and we need a function called union, hence called union find. Basically, what happens is that you have two nodes. So this union function takes two arguments. So it takes node 1 and node 2. And this find function just takes one argument, which is node. Find goes to this node, makes itself up to the parent node. And union just tries to connect two nodes together. And here's what's so nice about union find or disjoint set is that, for example, if there was 3 nodes, we're gonna call union on these 2 nodes, and we're gonna try to find its parent, right? Let's just say for this example, they were their own parents. That's fine. And we're gonna do the same thing for these 2 nodes, and the parent is going to be this one over here. And now, if we try to connect these 2 nodes, we're going to call our find function over here on this node and on this node as well. But their parent is the same node. That means there's a cycle in this graph. So once we find this cycle, we can just return true, and we can just return the index or the value of these 2 nodes. So that's basically how we're going to use union find to solve this problem. Now let's think about what path compression is. Okay, so let's just say that we're looking at this node right here. We called our union function on 2 nodes, and let's just say this node over here happens to be this node over here. So its value is x. So the parent of x is y. But that's actually not true, because the parent of x is actually this one over here. Let's call it node z. So we're gonna say if x's parent equal to parent of x, because remember, this root node is going to point to itself, making it the root node. So when we go from x to y, y does not equal to its parent. So we're gonna make this is the current parent, and the parent of this also does not equal to this node over here. So we're gonna make our way up and up until we find the parent or root node. But in this example, you can see that we're going one by one, and we don't have to do that. We can do what's called path compression. Basically, what we're gonna say is that parent of x, this one over here, is currently this one. But we're gonna say parent of x is equal to parent of x. Parent of x right now is this node over here. So this node's parent, meaning this one over here. So we're making our progression faster by doing path compression. So here's a picture I found from Geeks for Geeks. And visually, it looks way better than what I just drew. So I'm just going to use this picture. So as you can see, the initial node or the root node is 9 over here. And these are all of its children nodes. Basically, what path compression does is that it turns this structure over here and makes it like this. So next time, if we have to access this 3 over here. So if this 3 wanted to go up, this can just go up instead of going from here to here to here and to here. So instead of doing that, it just makes it a really short path to follow. So that's just basically what path compression is. It's a really nice optimization technique, and it's gonna lower our time complexity. Now let's jump into the coding. All right, before we actually jump into the coding, I want to talk about how we are actually going to initialize the parent and the rank variables that we're going to create. So in the beginning, we want to make sure that a node points to itself. So this node's root will be itself. So we need that information to begin with. And how can we do that? Right? So all the information we've given is the edges. For example, this node has an edge to here, and this node has an edge to here. So what we're basically given is x, y, and x, z. And the length of our input is 2, but as you can see, there are 3 nodes. And when we initialize, basically what we're gonna say is that we're gonna take the length of our edges, the input variable we get, and then we're just gonna add 1 node to account for all the other nodes, because if we don't, we'll be missing out 1 node. So after that, when we get this, we're basically gonna say, so this node, it points to itself, this node points to itself, and this node points to itself. And we can do the same thing for rank. So the rank of this node is going to be 1, and 1 here as well, and 1 here again. So that's how we're going to initialize our parent and rank variables. So in Python, we're just going to use a dictionary, and in Go, we're just going to use an array to represent this relationship. And the next thing I want to talk about is the time complexity. So just to find function itself, it would be O of n. However, since we're using path compression, we can say that the time complexity is O log of n. So union, on the other hand, since we're using rank over here, let's just say that in theory, the operation should take log of n time because we're using path compression to use find. But the time complexity of disjoint set using path compression and rank together, the two optimization techniques, it actually comes down to O of amortized n, and that's the worst time complexity. So with that being said, now let's go into the coding. So here's the solution to the problem in Go. So as compared to our Python solution, our Go solution is going to be a little bit more lengthy, and that's just one advantage Python has over all other languages because it's just so easy to write. Even so, in Go, it's not going to be difficult anyways. What we're going to do right now is that we're going to create a struct called union find or disjoint set. So let's call it type disjoint set, and it's going to be a struct. And our struct is going to consist of 3 things: parent and rank and the number of components. So we need the parent because we obviously need to know which disjoint set goes into which disjoint set. And we need rank because we are utilizing this technique called path compression, as we discussed in our drawing explanation. And we need n to know how many components there are within our graph. So now that's done, now we're going to define our functions find and union. So function find is going to receive a node, and that's going to be of integer, and it's going to return an integer as well. So here's how we're gonna do our path compression. While in Go, it's for, and one thing we forgot to do is that we're going to have to define this U variable over here, because we are going to be using this our disjoint set struct. So we'll be using this U variable, and it's going to be disjoint set. So while U dot parent of n does not equal to n itself, meaning that if it's not the parent of itself, then we're gonna do a path compression, which is now the u dot parent n is going to be u dot parent n, u dot parent of u dot parent of n. So that's basically what the path compression is. What's happening is that, so n is probably connected to other nodes, and then we're gonna say is that the parent of n is the parent of the parent of n. So we're basically shortening the path. So next time we iterate, we have shorter distance. So now we're just gonna say this n is going to equal to u dot parent of n. And if we have found the root of this node n, then we can just return the parent of n. And now we need to do the union function. So for union, we are receiving two inputs. We're receiving one node and two node. And it's going to return a Boolean value, because we know that as soon as we find a cycle in this graph, that's the answer we want to return. What we're going to say is that n1 root and n2 root is going to equal to u dot find n1 and u dot find n2 for that matter. And then what we're gonna say is that if n1 root equals n2 root, then we know that there's a cycle in this graph. So we're just gonna return false. The reason why we return false is this. So in our main function, find redundant connection, what we're gonna say is that first of all, we're gonna initialize our disjoint set. So our disjoint set is going to be disjoint set, and let's give it in the length of edges plus 1. And then what we're gonna say is that for I is 0 and I is less than the length edges and I plus plus, what we're gonna say is that if edges at I and if this 0, disjoint set dot union with, so we're gonna union edges I0 and I1. If this is false, then we're just gonna return an array of these two elements. And based on the description, we're guaranteed that we're gonna get an answer, at least an answer. But if we just leave it like that, Go is not gonna like it, so we're just gonna have to return an empty array like this, although it's not gonna get executed. So that's why we are saying if n1 root and n2 root equals, this is false. So what happens if this is not false? So now we're gonna use our rank to determine which disjoint set this another disjoint set goes. So we're gonna say if u dot rank of n1 root, if this is greater than n2 root's rank, then the parent of n2 root is going to be n1 root. So if this is the case, then u the parent of n2 root is going to equal to n1 root. Else if it's the other way around, then we're just gonna switch it up, and then we're gonna say that the parent of n1 root is n2 root, and we have another condition which is else. That's if these two are equals. If they're equals, like it doesn't really matter which one is gonna have higher rank. I'm just gonna say that n1 is going to have higher rank, and then we can update the rank of n1 root plus equals 1. So next time it comes, n1 root is going to have higher ranking than n2 root. Okay, so that's basically it. Now we just need to construct our disjoint set. So over here, I'm going to define a variable called construct disjoint set, and it's going to receive the number of components. And then it's going to return disjoint set. So parent and rank, they are going to be an array of integers with the length of n that we give it to. So that n is the length of edges plus 1. We went over why length of edges plus 1 in our drawing explanation, so you can go back and check why. And rank is also going to be the same. So we're going to do for I, so I is going to be 0, and while I is less than n, and then I plus plus, we're gonna say parent at this index is going to equal itself, and rank at this index is going to equal to 1, because all the nodes is going to have initial rank of 1. And at the end, we can just return a disjoint set of parent is going to equal to parent, rank is going to be rank, and n is going to be n. So that's basically it for defining and using disjoint set to solve this problem. Now let's run it to see if it works. Sorry about that. We don't need commas in here when we were defining struct. Now let's see if it works. We need to close our union function over here. Now let's run it again. And then because since we're returning false here and it's expecting us to return a boolean, we're going to return true over here. All right, now it runs. Now let's submit it. And yes, it works. So that's basically the whole intuition of using disjoint set to solve this problem. So if you've made this far into the video, thank you so much for watching. And if you liked it, please like the video and subscribe for eternal luck. And I hope you guys learned something new today. And if you guys have any questions, any LeetCode questions that you want me to cover, please leave a message in the comment section and I'll try to get it done as soon as I can. So I'll see you guys in the next one.